Welcome everyone, this is Derek Boyer, and I'll be teaching you Chapter 2 in Chemistry, up through the concept of pH. The basic concepts covered in this lecture will help you to understand microbiology in this course. Here is a curious chapter opening question that I hope you'll take a moment to read through, and I'll look forward to covering the answer to this question when we meet in class. We're going to take some time to understand the nature of matter. The atom is the smallest unit of matter, and when atoms undergo chemical reactions, they combine with other atoms to form molecules. These molecules build to form the structure and function of life itself. Atoms are composed of three main subatomic particles. Those include protons, neutrons, and electrons. Protons have a positive charge, and neutrons, as the name would suggest, have no charge. It could be described as neutral. And electrons have a negative charge. Protons are located in the nucleus of an atom, as are neutrons. They're found in the nucleus. Electrons, however, are not located in the nucleus. They're found orbiting around the nucleus. If you could take any of these subatomic particles and place them on a scale, we won't see about weighing them in grams, but rather we'll look at them as having units called atomic units. A proton is assigned a weight of 1 atomic unit. Similarly, neutrons also weigh 1 atomic unit. Electrons, however, are so light and so incredibly small that although they must take up some small amount of mass in terms of weight, it's so small that we're not going to choose to count that in this particular application of how we use chemistry to understand microbiology. We're going to assign a status of no significant weight for the electrons. So for our purposes, you can just say that they don't weigh anything that will count. In this diagram, we can see where the protons and neutrons are located inside the nucleus in the center of the atom. And then moving out from there, we can see the electrons that are occupying what's called the first energy shell or orbital. And then here we can see a second orbital, which would represent the second energy shell. This particular diagram was devised by Niels Bohr, a Danish theoretical physicist who won the Nobel Prize in physics about a century ago. And this is referred to as the Bohr model. There are hundreds of different atoms that are found on Earth and in the universe, and they make up the various chemical elements that are organized on the so-called periodic table of elements. And each element is organized by what's called atomic number. And the atomic number is what gives the element its identity as in how many protons that atom has. For instance, element number 1 is hydrogen, which has 1 proton. If you were to add a second proton, it would no longer be hydrogen, it would become something called helium, and so forth. So in addition to that, we'll be looking at mass number concerning the elements, and this is where we would take not only the protons, but then add in the number of neutrons to get the mass number, which is a relative weight of a given element. The atomic symbols are going to be letters that refer to the elements, like a capital H would be for hydrogen. For helium, it would be capital H, little e, and so forth. Isotopes are another aspect that we'll be taking a look at here within any given element, where if you look down here, oxygen will always have an identity defined by the 8 protons, the number 8 here in all 3 of these so-called isotopes of oxygen. And when we look at the top number, which is going to be the mass number, that is going to take into account the number of neutrons as well. And so what we see here for oxygen 16 is that if there are 8 protons, then there must be 8 neutrons that make up its total mass number. So here we can write that down, that oxygen 16 has 8 neutrons. And then a different isotope of oxygen that differs by 1 more neutron would be oxygen 17. So we could take the number 17 and minus out 8, and we see that there will be 9 neutrons present in oxygen 17. And finally, we have oxygen 18 that's listed here. And once again, it has 8 protons that defines it as oxygen, but then 10 neutrons. As an ending note on this topic of isotopes, it would be important to take into account that isotopes can give off sometimes radioactivity. So oxygen 17, oxygen 18 with these additional neutrons can give off a signal that then can be tracked within living systems. And this becomes important in molecular biological research as well as some types of medicine where radioactive isotopes can be put into a patient and that signal then can be tracked through their organs in order to assess a person's functioning and health. Taking into account what we learned from the previous slide, we can apply some basic rules that atoms in general can gain or lose numbers of electrons. They can lose excess neutrons, but they can never gain or lose protons. Remember, if the number of protons differs, then the atom changes its identity and becomes a different element altogether. This figure from your textbook is showing some of the various elements that make up life itself. And there's no need to memorize this. However, it does show us the differing numbers of protons so I was mentioning before, hydrogen has 1 proton. Carbon is defined by having 6 protons, as nitrogen then has 7, and oxygen has 8, and so forth. The approximate atomic weight would be what I referred to earlier as the mass number, where the protons and then the neutrons would be added together here to make the approximate atomic weight. Also, one thing of note is that most of life as we know it, if you just broke it down to pure elements, would be composed of over 96% carbon, hydrogen, and oxygen and nitrogen. These 4 elements are what life is made of for the most part. In the next few slides, we'll take into account where electrons reside within a given atom, and we'll be specifically looking at electron shells and also then their corresponding energy levels. On this slide and the next slide, we'll see that there are tables showing us various electronic configurations, and let's take a closer look here at some of the common elements in this regard. So hydrogen has one proton that gives it its identity, and that has a positive charge, and it's balanced out here by one negatively charged electron, and this is how hydrogen exists. There is an empty open circle here down below, and this would represent where the first electron shell could technically accept up to 2 electrons to fill that energy shell or electron shell. For carbon, which gets its identity from the 6 protons that are in the center of the nucleus, they carry a positive charge, and therefore this carbon is presented as having 6 negatively charged electrons that balance out that carbon nucleus with the 6 protons. So we have the first energy shell is full with 2 electrons, and then the second energy shell here has the other 4 electrons, negatively charged electrons. However, it's noted that the second electron shell can accept up to 8 electrons before it fills up. And so we see 4 open circles here where more electrons could be accepted. And this is where carbon would find an opportunity to bond to other neighboring atoms or elements, as we'll see in some examples here in the future. This part of the table takes us from the second energy shell and its illustrations for nitrogen and oxygen elements. Nitrogen showing 3 empty spaces where electrons could be added and bonds could be formed around nitrogen. Oxygen showing 2 places where bonds could form around an oxygen atom by accepting more electrons. But then now looking at magnesium, we can see that the first energy shell and then also the second energy shell are completely full, and that now a third energy shell is added on to accommodate additional electrons that we can see here. If we look at the third energy shell or electron shell, it could accept up to 8 electrons as well. So in chemistry, for these energy shells, second and third, we call this the octet rule because they both would seek to gain up to 8 electrons to become most stable. Now that we've established a basic understanding of atomic structure, we can look at how atoms can combine with other atoms to form molecules. And molecules are going to form according to how the outermost shell of electrons interacts with another neighboring atom. And a key term here is what's called valence. And valence is referring to the outermost shell. And so then we can talk about valence electrons that are in that outermost shell. And typically we can say that electrons can be lost out of that shell or they can be gained. And this is all going to be in a way that contributes to stability of a molecule or an atom. When chemical bonds form, it's due to electron configuration rearranging. And so we're going to be taking into account 3 major types of chemical bonds, and those include ionic bonds and covalent bonds and hydrogen bonds. Ionic bonds are formed through ionic interaction, where atoms or molecules ionize. An ion essentially is something with a charge. So we can talk about atoms having a charge, if or molecules for that matter. If an atom or molecule has a positive charge, it's referred to as a cation. And oppositely, there are ions that have a negative charge called anions. And one thing we need to keep in mind whenever we talk about charge interaction is that opposite charges attract. So cations and anions, positive and negative charges, will then bond together to form ionic bonds. Ions form when electrons move around. So here on the left, we have a sodium atom that is not an ion at first. But when we look at sodium's electronic structure, there's one lone electron in the outermost shell, the valence shell, if you recall. And that one lone electron is most easily just lost from sodium so that sodium can become a positively charged cation with a stable outermost valence at this point, meeting that octet rule. However, looking back at that lost electron, it has to go somewhere. So this electron in this diagram is showing that chlorine, a neighboring atom that can very easily accept that electron, could take that on. And when we look at chlorine's valence, it has 7 electrons in its third energy shell. And so that empty spot right there can easily be filled by the electron that comes from the sodium. And so then once that electron is gained, chlorine becomes the chloride ion, which has that extra electron. Now this is an anion because now chlorine has gained one excess minus charge. So chlorine at its center in its nucleus has 17 protons, but pictured here now, it's gained an extra electron, an 18th electron, which then gives it a net overall charge of -1. Meanwhile, going back to sodium, it lost an electron. In its nucleus, it still has its 11 protons that defines it as an element, yet it only has 10 electrons. So one minus was lost and has an overall net positive charge of +1. And so then sodium and chloride can combine to make what we know as table salt. In the first 2 points, we see that atoms with few valence electrons will tend to lose them in order to gain stability. And on the second point here, we see that atoms that have almost 8 electrons, when we think about the octet rule, for instance, will tend to gain electrons to get to that magic number 8. Ionic bonds are said to be common in inorganic molecules. An example of an inorganic molecule would be sodium chloride, otherwise known as table salt. And when table salt is dissolved into water, so-called electrolytes will form. Electrolytes are defined as ions that conduct electricity, but without the movement of electrons. So when we think about electrical energy or electricity, we think of the movement of electrons, like through copper wires, if you're talking about a physical appliance or something that's operated by electricity. But in living systems, electrolytes are key to biochemical reactions, and they drive They use electrical potential. They conduct electrical potential to drive key biochemical reactions. Some examples of electrolytes in living systems are sodium. So when sodium chloride dissolves, like table salt dissolves, it will separate into Na plus and then Cl minus. Also, other common electrolytes are potassium, which is represented by the letter K with a +1 charge. And then there are a couple of other divalent or +2 charge ions that participate as electrolytes in living systems. You have magnesium with a +2 charge as well as calcium. In this illustration, we see the formation of sodium chloride forming table salt. So here's your sodium ion, opposite charged chloride ion forming to make this ionic bond. But keep in mind that this could be fully reversed and the ionic bonds can dissolve in the presence of water. And then the crystals of salt would dissolve, and then you would end up with chloride Cl minus floating around as an anion, and the sodium plus cation as well, floating around as electrolytes. Moving on from ionic bonds, we can now look at a second type of bonding, covalent bonding. Covalent bonds are where two atoms will share pairs of electrons, one or more pairs. And we can see here in this example that a hydrogen atom, for instance, could pair up with a neighboring hydrogen atom. And because each hydrogen has one lone electron, it could then pair share. And so then you can see here in this visual that this would help this shared relationship to satisfy stability, where the first energy shell can have up to 2 electrons. And between these two hydrogens, they can then be more stable together than they are when they're apart, like we see over here. And these covalent bonding relationships can be written shorthand as a single dash mark, like we see here, H dash H, or then over here, the molecular formula is written H2. Covalent bonding is not limited to atoms of the same type always associating. Here we can see that carbon, which is one of the most versatile of all atoms for covalent bonding, can form up to 4 covalent bonds, because in order to meet its octet rule, it could gain an electron at 12 o'clock here to pair up to make a bond, or 3 o'clock, or 6 o'clock, or 9 o'clock here, so to speak. And each one of these positions could be occupied by hydrogens, lending their electrons to make this possible. So what we see forming here is a molecule of natural gas known as methane. So methane, a carbon with sharing electrons with 4 different hydrogens, can also be shorthand written as single dash lines, or then the molecular formula here, CH4. All right, in this slide, we see that covalent bonds are not always singular relationships. On the top of this diagram, we do see an example of one shared pair of electrons, which could be written as just a single bond between 2 atoms like carbon and carbon. But down below here two pairs of shared electrons can exist, and so you could write here a carbon-carbon double bond, and it's even possible for there to be a carbon-carbon triple bond type of relationship, but because the triple bonding is not observed in living systems, we'll go ahead and just focus on these two that we see here. And one more thing of note, carbon-carbon double bonds, or the more shared pairs of electrons, the stronger the bonding relationship there would be, the harder it would be for these to break. Okay, we're on to our third bonding type called hydrogen bonding, and this is the weakest bonding relationship of the three types of bonds that are covered today. And so we on the left here in panel A, we have a single H2O molecule. And keep in mind, the hydrogens in H2O that are bonded to this oxygen are represented here by these solid lines that have arrows pointed towards the oxygen nucleus. And the reason for this is that these are actually covalent bonds here, not hydrogen to begin with. And so let's label these. And remember, covalent bonds are shared pairs of electrons. And so I'm just drawing in little dots here, showing where these pair sharings take place for the covalent bonds within a single H2O. All right, but if you look at this, oxygen is a very large atom, and it's called a highly electronegative type of characteristic that unevenly pulls the electrons away from the hydrogens and towards its nucleus. Now, if you look, these negatively charged electrons are headed inward here, but then on the outer portion of the hydrogens on the left here, there is a partial positive charge because the electrons are, diving towards the center of this, and then towards oxygen. And likewise, the same thing is going on here in the right. And these are what are called partial charges, and partial charges are denoted by looks like a number 8, but with a tail missing, or an S with a really long lower part there. And so this denotes what's called partial charge. So I'll write that down. Okay, this symbol here is referred to as a partial charge, or denotes partial charge. And if we look at this other side of the H2O molecule, don't forget there's also a negative charge, partial charge characteristic going on here. And the way that this can be explained is that oxygen in its valence has a couple of unshared pairs of electrons hanging out here on this side. So if you were to scan around on this single oxygen, this single water molecule, this side of oxygen would have partial negative charge character. So overall, we can say that one water molecule has a polar nature to it. There's a polarity, minus charges over here, and positive charge characteristics here, and over here as well. And so then now, if we take that into account, that water has this polar nature to it, then we can see here that multiple water molecules can interact with one another through these dotted lines that we see here. And these are the hydrogen bonding relationships where the partial charges of one water molecule, partial positive charges, can be attracted to the partial negative charges of other water molecules. So one single water molecule could form up to
Well, let's see how many hydrogen bonds. So right here, we see that there's one water molecule forming up to 4 hydrogen bonding relationships around it by neighboring water molecules. The way I think of these is they look a little bit like Mickey Mouse shapes. You've got the head, which is the oxygen with the partial negative charges, and then the ears make up these partial positive charges. And so the head or the chin of Mickey Mouse on one water molecule could be attracted to the ears of another, and so forth. And this dictates how water behaves as water molecules tend to stick to one another. And but keep in mind there are other types of hydrogen bonding relationships where nitrogen, which behaves a bit like oxygen in this type of electronegative or slightly negative relationship, could play a role. Here we don't see nitrogen involved, but there are instances where we'll see this in the future. Other key points to keep in mind with respect to hydrogen bonding relationships is that hydrogen bonding may not only be between molecules of water like we saw in the previous slide, but sometimes hydrogen bonds can form as relationships within a single molecule. Like a very long protein, for instance, could have multiple hydrogen bonding relationships that help to form its structure. Hydrogen bonds, because they are weak, can be easily broken, as mentioned here about temperature and pH variation, disrupting those kinds of bonds. And in addition, hydrogen bonds are a key part of orienting amino acids within a protein. Amino acids are building blocks of protein structures, and then nucleic acids can have a building block called nucleotides, and hydrogen bonding can occur there and help to result in the characteristic shape of DNA with its ladder type formation. And we'll more on that later. We'll look at that, and then we can see here it says results in three-dimensional shapes of proteins. So proteins are these complex globular structures, and hydrogen bonds play a crucial role in the shape and function of proteins. Since water is such a special case with respect to how it behaves under the influence of hydrogen bonding, I'd like to spend an extra moment on it here and ask this key question. So, why is ice less dense than liquid water? So, let's think about ice. Ice is a solid substance, it's solid water, right? Frozen into place. Now, typically when we think about solids, we think of them being the most condensed, the heaviest, right? So if you put a solid into a liquid, for instance, it should sink. It should be more dense and sink to the bottom. However, what we know through life's experiences is that ice, which is, a solid form of water, when you put it in water, it will float, right? Because in fact, it is less dense than the liquid water that you floated in. So why is that? Let's look over here. If you look at hydrogen bonding according to temperature, hydrogen bonding is most numerous and prevalent within liquid water. And the cooler that water gets, the more condensed and more cohesive the water becomes. But then something very, very strange happens when we get down. Something surprising happens when we get into the freezing of water, which is where hydrogen bonding will lock into place and form crystallization. And because the hydrogen bonding has the geometry that it does, it creates this expansion. And so we see that ice will expand as it freezes into place and those hydrogen bonds become locked, as we see here in this crystalline structure down here below. And on the opposite end of the spectrum, if we heat water up and that keeps disrupting progressively more and more hydrogen bonds, we can get up into these areas up here where we see towards boiling then that all the hydrogen bonding is disrupted and individual little water molecules go floating away into the atmosphere as a gas. So to answer this question, we can write down that why is ice less dense than liquid water? Quite simply put, hydrogen bonds, right? Hydrogen bonds will be locked, frozen into place. This takes up more space. Become less dense. Okay, very good. Another property of water's behavior with respect to hydrogen bonding has to do with the explaining the answers to these questions as well. So this question up top here says, what causes capillary action to occur in these tubes? Now, let's look at capillary action. Capillary action is the way we refer to water's tendency to creep up a a narrow tube when placed in water. So tube A here on the left, the water creeps up quite a bit above the um, level of water here in the beaker. And then tube B, which is a lot wider, will have a lot less water creep, so to speak, here in this illustration. And so we're asking, why is that? And for quick reference, another thing that can be pointed out here is this is what's referred to as the meniscus. It's a U-shaped formation where the water creeps up just a little bit on the sides, and we're getting just a tiny bit of capillary action in this case, but with this characteristic shape referred to as the meniscus. Give myself more room here. Meniscus. And when we measure in the science lab with the meniscus, we always measure to the bottom of the meniscus. And we don't take into account that this extra liquid here creeps up the sides. We measure to the bottom of the meniscus. Here, the capillary action it may be difficult to see any kind of U shape, but technically that would be a little meniscus there as well. And so going back to the original question though, what causes capillary action is that water can hydrogen bond to glass. And so let's take time to mention this. Water, and I'll abbreviate hydrogen bond as H bond. H bonds, hydrogen bonds to glass. And so the second question here is then key. Why does the water travel higher in the thinner tube? And if you think about this for a moment, it has to do with the fact that there's more contact between the water and the surrounding glass tube with respect to, how little space there is here. By comparison, we look here, there's a lot more water in the middle of this column that's not in contact with the glass. And so there's less opportunity for a lot of the water molecules that are out of contact with the glass to make contact. And so therefore there's less travel, there's less creep up this test tube. Capillary action depends upon there being more contact with the glass. The narrower the glass tubing, the higher the hydrogen bonding relationship would be driven up here and making capillary action go higher. So how should we put this? The thinner tube creates more contact with the water, hydrogen bonding to the glass. The surrounding glass. Okay. And this is relevant within living systems, although we won't see this so much in microbiology per se, but this second concept down here about the thinner tubes exists more in examples of like trees. So they're very thin, narrow, naturally occurring tubes that carry water and sugar up through a tree from the roots all the way up to the leaves and through the trunk of the tree. We have what are called xylem and phloem type structures that take advantage of this capillary action and this hydrogen bonding within a living system that allows plants to grow very tall and to survive based on this dynamic. Okay, let's review the three bond types that have been covered in this lecture. Starting with over here on the left, panel A, we have an atom here and then a neighboring atom over here. And these two atoms appear to bond together while sharing a pair of electrons, a single pair of electrons. And then down here we have another example where one atom and a neighboring atom, when they fuse to combine, they actually appear to be sharing two pairs of electrons. And so these two configurations, referred to as single and double types of bonding relationships with shared pairs of electrons, would be called what? Let's take time to write this down. The term is covalent. So think of co as sharing, and then valent are referring to those electrons in the outermost shell, and they're sharing these pairs of electrons to fill their valences, to stabilize together by sharing. Secondly, in the panel B of this illustration, we have an atom here on the left, and it appears to be giving up an electron. And when one of them, this minus charge electron leaves, it now takes on a positive charge. And when that electron travels over to this atom here that gains it on the right, now it's gaining an electron minus charge. So now, in fact, it has a overall net charge of -1. So we have formation of positive and negatively charged ions. And if you recall, the special names are the cation for the positively charged ion, and then we have the anion, which is the one with the negative charge. And together, the cation and the anion form, you guessed it, an ionic bond. Okay, we get the ionic bond there, with the covalent bond here on the left. And then finally, by process of elimination, you could say the last one is the hydrogen bond, also sometimes referred to as an H bond for short. But let's see why. Let's not just, say, oh, well, we guessed it. But first of all, our first clue would be the dotted line. So we see the dotted line. That's how we denote the hydrogen bonding. And we see that there's a partial positive charge that's going on here from this hydrogen because of its proton hanging out here. And then up here, we can see that electron being pulled towards a larger atom that's probably something that's highly electronegative. Speaking of which, down here we have a highly electronegative oxygen or nitrogen that has some partial negative charge characteristic here, and so the hydrogen is attracted to that, and we get a weak hydrogen bonding relationship like pictured here. Now that we're done reviewing bond types, I want to move on to a concept about understanding molecular weight and moles. Now, for this course, we're not going to focus so much on moles per se, but we'll at least review the concept as it corresponds to defining or measuring molecular weight. Okay, so let's take water for an example. So water's molecular formula is H2O. And if we go to the periodic table of elements, we look at hydrogen, it has a mass of one, a weight of one, and that's for the one proton. Remember, the electron doesn't count as weight in our calculations. So you have two hydrogens times one proton each gives it an atomic weight of 2. And then we have oxygen. Now, oxygen has 8 protons, but also 8 neutrons in the ordinary oxygen called oxygen 16. So here we have the mass of oxygen being 16. So if we add these two together, we get a total molecular weight of 18. Water has a molecular weight of 18. Now, if we were to take water and measure it on a scale into the amount of 18 grams, which we could measure out in a beaker, we would get what we would refer to as 1 mole of water. All right, now in your chemistry classes, you'll learn about that a mole has a certain amount of molecules in it, referred to as Avogadro's number, 6.02 times 10 to the 23rd molecules of water in 18 grams that you measure out in the scale. We're not going to worry about Avogadro's number, but what we want to keep in mind here is that water itself is a relatively small molecule overall. It does not have a very large molecular weight, especially when compared to items like carbohydrates and lipids and proteins and nucleic acids such as DNA or RNA, and their molecular weights are enormous by comparison. So just keep in mind that the relative size of a molecule or a substance plays a big role in predicting what's going to happen in living systems and how life deals with these molecules and utilizes them. All right, it's time to get into understanding chemical reactions. When bonds form, the reactions that take place, or when bonds break, we're going to take into account here. And typically, if we look down here at this term endergonic, that would refer to where energy is being absorbed, typically when bonds form. On the reverse side of this, conversely, we have what are called exergonic reactions, in which energy is released, and this would be typically when bonds are broken. And so the energy could be thermal energy, but you can also talk about these reactions as releasing other energy as well. There can be light energy. Um, there can be kinetic energy, and so energy in general, though, whatever form it's in, will be referred to then as endergonic if it's being absorbed, or exergonic when it's being released. One fundamental type of chemical reaction are what are called synthesis reactions, and in this case, we can see molecule or atom or ion A would then be combining with B, forming a bond to then become this final product here, AB. So let's take note of this. In a synthesis reaction, uh, bonds form, right? A bond forms. And I want you to think about when a bond forms, energy has to go in to building that building, to forming that bond. And so we're going to apply the term endergonic, with energy being put in to build that bond. And this is a form of metabolism that is referred to as anabolism. And so think about reactions that build as being anabolic. So I think of like a bodybuilder. If a bodybuilder takes anabolic steroids, they're trying to build up their muscles to the biggest they can be. They're building, they're synthesizing more muscle. They're putting a lot of energy into uh, those reactions. The reverse of a synthesis reaction is what's called a decomposition reaction. And so here we start with AB to begin with. And if AB breaks apart, then A will be released and B will be released separate from one another. And let's take a couple of notes on that, just like we did on the previous slide. But with decomposition, now a bond breaks. And when a bond breaks, this is going to typically result in an exergonic type reaction where energy is released. This represents a form of metabolism called catabolism. And catabolism is, the way I remember it, is to think of something like a catastrophe. A catastrophe may sound a little violent, but the idea would be that if things blew apart all of a sudden, if a bomb went off and a bunch of bonds were broken, enormous amounts of energy would be released and everything breaks apart. And so you'd get a decomposition. The third type of reaction is what's called an exchange reaction. And let's do some describing and labeling of exchange reactions. First of all, it's a combination of a synthesis that we first learned about and a decomposition. Really, you get two things happening at once. And we'll walk through how this is true. Okay, so on the left, we have NaOH, and this is known as sodium hydroxide. And if you know a little bit about chemistry, as we're beginning to learn, um, there is a concept called pH that'll be covered very shortly in a few slides. And the pH of sodium hydroxide is basic or alkaline. It has a high pH and it's a strong base. And when it's mixed with HCl, or if it's put into the same environment, HCl, which is known as hydrochloric acid, which is the kind of acid that's in your stomach, it's a very strong acid, will react with the sodium hydroxide and an exchange reaction will occur. Let's see how this works. So let's look at the sodium hydroxide. Here's sodium, the Na, and when this goes into solution, it can ionize. And so Na plus could form in the water, and it can travel over and seek out its best friend over here, um, chlorine, which also can ionize, and then that becomes chloride, right? So NaCl forms over here. We see this uh, product form. And then meanwhile, there is an exchange going on because um, the hydroxide that's here, the OH, this can seek out this hydrogen here. And so OH, which takes on a minus charge, will be attracted to H, which takes on a positive charge. And we don't see this the charges forming here, but we can kind of just imagine this happening, and so H and OH will create ultimately water. And so this really strong reaction between sodium hydroxide and hydrochloric acid, after what's called neutralization, you end up with salt, just ordinary table salt, NaCl, and water. And that's just one example of an exchange reaction where we're seeing this synthesis and decomposition reactions taking place simultaneously. The last type of reaction that we need to know about is the reversible reaction. These types of reactions can go in either direction. And although we see here that A can combine with B to form AB, this can also travel back in the other direction, depending primarily upon whatever the prevailing conditions are. So in this case, we're seeing that if there's excess water, moisture, that A and B can proceed to form this bond, AB. But if heat is prevalent, then you would imagine that that could actually involve water loss. And under heated conditions, then it's showing that AB could break apart and decompose back into separate A and separate B. But there is a reversibility about this depending on which conditions prevail. One thing that I would like to point out, in addition to what's illustrated here, is that sometimes you get where one arrow is bigger and another arrow is smaller, like that. And so reversible reactions don't necessarily have to be 50-50. Sometimes one direction is favored more than the other. And in fact, another way that these kinds of reactions can be represented is to put a really large arrow head on one side, like this, and then on the other you could put a small arrowhead like that. So these are just different ways of specifying where maybe one direction is favored most in terms of there being an unequal equilibrium of sorts, but nevertheless still reversible. Another key concept in chemistry and biology are redox reactions. And so this is really just a combination of two words, reduction and oxidation. And when we pair these together, we refer to these as redox. And so the key here, if you may have learned this in a chemistry class, I'm going to remind you or teach you a way to remember what is oxidation and what is reduction. Now, the definitions here says oxidation releases electrons, and reduction is where electrons are received or gained. And so a handy mechanism for this that is helpful is what's called oil rig. OILRIG. And the way that oil rig helps us is that it stands for oxidized, oxidation is lost, and reduction is gained. And so we have this abbreviation, oil rig. This acronym, oil rig, right? So what is being lost? What is being gained? Keep that in mind. It's electrons that we're tracking here. And electrons are sometimes abbreviated E minus. So that's another way to refer to an electron is, or to shorthand denote it as E minus. And let's track that here in this illustration. So sodium has an electron that it can give away. And chlorine has an electronic configuration, a valence that's missing one electron in it, would love to pick that electron up. And so ultimately, when we look at sodium and chlorine, how does this work? Sodium loses an electron. So sodium, what happened to sodium? Sodium became oxidized. Okay, because remember, oxidation is lost. So sodium lost an electron and became oxidized. And in this world of redox, as we're seeing here, it's the chlorine that gained an electron and became reduced. And so chlorine became chloride, and there's your redox reaction. Let's take time to define these two key terms, organic and inorganic. So compounds that are considered organic, according to our book, are compounds that contain both carbon and hydrogen at the same time. So organic contains both. Let's underline the word both just to make sure we know it's both C and H simultaneously. On the other hand, inorganic does not contain both carbon and hydrogen at the same time. And how does this work then? What's an example? With or inorganic, an example would be about water. So water has H2O. It has hydrogen, but there's no carbon. And so it would be considered inorganic. And that would be the most common example of an inorganic compound. Sodium chloride would be another one. There just isn't both carbon and hydrogen present in those compounds. Let's revisit water's properties for a moment before we head towards defining its role in pH and its ability to act as a solvent. It has to do with polarity here. So remember that within one molecule of H2O, you have a couple of pairs of electrons that are being pulled inward, away from hydrogen and towards oxygen's nucleus. And remember that hydrogen has a proton at its nucleus, and so then we can see here on the outer edges of the hydrogens that there are going to be these partial positive charges. And then up here on the top side of this figure, we can see that oxygen will have these unshared pairs of electrons sitting here, and this is going to give partial negative charge properties, characteristics here. So water has this polarity about it, and it hydrogen bonds with other water molecules. It can absorb a lot of temperature, and not, or it should be absorb a lot of energy and not change temperature easily. And also, in addition, water is one of the it's one of the most prevalent substances within life forms, including the human. We're way more than half water, just water weight, and so that can vary depending on your age. When you're newborn, it could be as much as 75% of your body would be water, and as we mature, it could go down to about 2/3, as indicated here. Here we see an illustration of how water can act as a powerful solvent. So water as a solvent functioning to dismantle some sodium chloride crystals. And how does this work? So let's look at the dynamic. Water being very polar. You can see the negative charge characteristics of oxygen right here is attacking the green circles here. The green balls are the sodium ions, and so sodium separates, and its positive charge interacts with these negatively charged portions of the water molecules, and then the partial positive charges, like the ears of, like I was saying, like a Mickey Mouse kind of shape, those are going to interact with the negatively charged chloride ions that get pulled away and ionized into solution as water just completely dissociates and dissolves the sodium chloride. Water also plays a key role in biochemistry where H2O can separate. So if you have water here, H2O, and then it separates into H plus and OH minus, then these components of water can go into systems of biochemistry. So if you have R and R prime, and they're bound by, these two things are bound by a single covalent bond. R, by the way, stands for radical. It just means variable. Like this could be X and Y if you like, but this compound, when water is put into a reaction here on the left, the OH could then be used to attach to R, and then the H attaches to R prime. And a real living example of this would be something like maltose. Maltose is a disaccharide sugar. We're going to talk about how if you take two simple sugars called glucose, and if they're bound together by a covalent bond, then you have maltose. But water can be used to split that apart, and then what's born out of the other side of the reaction would be two separate molecules of glucose. See how the water essentially just disappeared as it was added to this reaction to bear out these two glucoses that are produced. If we do a little bit of math with the chemical equation that we saw in the previous slide, we can do some inventory here and see, okay, so the molecular formula for glucose, which is a simple sugar that's found in our blood, like our blood sugar, its molecular formula is C6H12O6. And maltose, which is made of two glucoses, as we can see here, is going to be then two of these, right? So we add these together and we get a C12, H24, and then O12. And so that would be the total numbers of carbons, hydrogens, and oxygens. Interestingly, though, the molecular formula for maltose is actually C12H22O11. And so if we do a little bit of subtraction from the total that we have here minus the maltose, what is the difference? So let's take time to write that down. It's pretty simple. The H24 minus the H22 gives you H2, and then O12 minus O11. And there you have it. You have water being the difference. Water makes the difference in many reactions. Okay, everybody, we're in the final stretch. We're going to spend the remainder of the slides defining the basics of what is acid, how is that different than a base, and how do acids and bases compare to salts. And just as a quick preview, acids always result in releasing hydrogen ions, denoted here as H+. Bases will release hydroxide ions, OH-, and then salts do not have an effect on pH. Notice the sodium plus and chloride minus have no effect really in any direct sense on H plus or OH minus release. We don't see that happening with salt. So salt doesn't affect pH, but we'll still just show how that is true. Looking more closely at the definition of an acid, it shows here that an acid is any substance that releases H+, also known as hydrogen ions or protons, into solution. Let's take time to write that down. So an H+ is also known as a proton and also known as a hydrogen ion. They're all referring to the same thing here. And mathematically, pH is measured on a scale of 0 to 14. And right in the middle of this scale, 0 to 14, we have 7. Now, 7 would be neutral, but it's saying here that a pH of an acid is defined as less than 7. Right? So an acid is less than 7, below 7. And so there's acid. Let's move on now to base. Bases are defined as substances that release OH minus in solution. So what is an OH minus? It's called a hydroxide ion. And what we want to keep in mind about a hydroxide ion is that the OH minus would have the ability to combine with an H plus and reduce how many H pluses are in solution, because when you combine an OH minus with an H plus, you're going to get water essentially. But let's write down here that anything that is a base or any solution that's basic, okay, is going to be above 7. As a pH value. Let's touch on salts for a moment with respect to pH. So first of all, salts do not release hydrogen ions or OH. Therefore, they don't affect the pH directly, or we're not looking at them in terms of them being acidic or basic. So for our purposes, realize salt, like NaCl, does not change the pH. However, we know that salts are very important for dissolving into water, forming ions like Na plus and Cl minus, which can act as electrolytes. And if you needed a reminder of what electrolytes are, they are ions that have an important role in conducting electrical potential that could be vital to biochemical reactions. So, it's kind of complex. I'll write that down again. Electrolytes are ions that conduct electricity or electrical potential, if you will. And they facilitate essential biochemical reactions. I'll put here many biochemical reactions. Further defining pH, we can work towards understanding the numerical value and how these values come up on a scale of 1 to 14. So if we take a look here, there's a little p and a capital H. And one way we could think about it, without the numbers at first here, is just to say the power of hydrogen. But mathematically, this power, so to speak, is this, where the little p comes from in physics and in chemistry. It actually is an abbreviation or shorthand for negative log function. And then the H is in reference to hydrogen ions, H plus ions. So we're mathematically, taking the negative log calculation of hydrogen ions. And then these brackets are really important too. The brackets around that are referring to concentration. So let's take time to write this all down about the brackets. First of all, if you're not familiar with the shorthand, if you put brackets around something, it means concentration of. So if you put an X in there, it'd be like concentration of X. In this case, if we put the hydrogen ion in between the brackets, then we get the concentration of the hydrogen ions, all right? But then we're taking the negative log. Now, that function isn't very intuitive in a direct sense for the way we think, like, some things are directly proportional. In this case, though, when you take the negative log of something, it becomes inversely, it has an inverse relationship. So if we see numerical values that are below 7, as I said, that's acidic. So acids are where there's an excess number of hydrogen ions. Let's write that down. Okay, so here's where you kind of have to think about this. More hydrogen ions going up is going to lead to a lower pH value. Okay. Less hydrogen ions going down is going to equal a pH value that climbs. So we're seeing here this inverse relationship. It's important that everybody remember that when thinking about pH values, so that it makes sense when you think about this pH scale. On the next slide, that'll be our final slide for this lecture, is we're going to look at some examples and see how these pH values are higher or lower numerically according to acids and bases with some common examples. So let's do that now. Okay, so let's finish off with some common examples of substances that we would have heard of in terms of how they relate to acids and bases, or even a neutral pH for that matter. So up here at the top, we see a beaker with a bunch of pluses floating around, and this is supposed to denote an acidic environment. Okay, this is an acid because it has excess hydrogen ions floating around. That's what those little pluses are. Okay, now in the middle here, we would see that if there are equal amounts of minuses and pluses floating around, we get a neutral solution. And then down here where we have excess minus floating around, that's actually going to be the minus signs that are here representing the basic solution influenced by excess OH minus floating around in solution. And in turn, those hydroxide ions, the OHs, are going to absorb, hydrogen ions and cause the pH to go into the alkaline range. And so numerically here, let's see if we have 14 and then 13 and 12. Probably should have pre-numbered this, but let's just go ahead and give this some quick work. Okay, here's 7. Okay, there's neutral, right? And then 6, 5, 4, 3, 2, 1. And then I guess 0 at the very end there. Okay, so pure water. We'll just put it right here at neutral. Okay. And then what are some common substances that we could relate to? So hydrochloric acid, like stomach acid, we'll put here as one of the strongest acids that we observe in living systems. And out there in the everyday world, HCl is standard. And then on the opposite end of the spectrum, we have sodium hydroxide, just pure NaOH. And things like oven cleaner, is a common way of referring to sodium hydroxide content, almost purely. It's called lye, or oven cleaner. And then maybe you guys have heard of ammonia. There's another strong base. It has a pH of somewhere between 10 and 11 when tested at room temperature. Ammonia. And if you weren't aware, the molecular formula for ammonia is NH3. And I wanted to take time to point that out because you're going to see ammonia talked about both in lab and lecture at different times, because that's a pretty strongly basic substance within living systems. Ammonia. It is technically a weak base in the chemistry lab, but for living systems, that's well above 7 and pretty powerfully basic. Let's see what else could be above 7. Milk, but not by much. It's just above 7 in that range. There aren't too many alkaline substances that we're going to get into here. Right below 7, typically urine will have a default due to things like, uric acid being present. Sometimes urine can go into the basic range depending on your diet, but I'll leave it right there, just typically below 7. Also in this acidic range, as we go down the list, you'd find things like lemon juice. Lemon juice is pretty sour and sharp. Tomato juice be also very acidic, not quite as acidic as lemon juice, but kind of down there in that range. Um, yeah, and we could fill in the blank with some other things that are acidic as well. Um, but this at least gives you some common examples of things that can be very acidic. Vinegar would be in here somewhere as well, acetic acid. I don't want to fill this up too much. I think this gives us a general idea, and I think it's a good finish. We made it. Hooray. Thank you for tuning in and learning these basics, reviewing them, being ready to jump in and do some more exciting parts of chemistry and biochemistry where it gets to be a lot more interesting. So looking forward to that. Thanks, everybody.